Right now, somewhere online, a headline is telling you a star just screamed and Voyager 1 heard it happen, as if some distant sun suddenly erupted in agony and a nearby spacecraft caught the sound. Here's the truth nobody wants to slow down and tell you. The star doing the screaming isn't some distant exotic object light years away. It's ours. It's the sun. And the scream isn't a metaphor dreamed up for a headline. NASA's own scientists have used almost exactly that language on the record for over a decade to describe something Voyager 1 has been picking up from more than 15 billion miles away. A sound so strange that when engineers first converted it into something human ears could actually hear, they didn't know quite how else to describe it. Because the sun doesn't just sit there quietly burning. Every so often it erupts violently, throwing enormous clouds of superheated plasma out into space with enough force to eventually cross the entire solar system, blow past every planet, and keep going for billions of miles into the dark beyond. And out there, in the space between stars, something genuinely strange happens when that eruption's shockwave finally catches up to a 50-year-old machine that's still, somehow, listening. This is the real story of what Voyager 1 actually detected, why NASA's own scientists reached for the word sing to describe it, and what it tells us about a part of space no human instrument had ever been able to listen to directly before this spacecraft got there. Start with what actually happens on the sun to set an event like this in motion. Every so often, the sun's outer atmosphere becomes unstable and releases what's called a coronal mass ejection, an enormous cloud of magnetized plasma, sometimes containing billions of tons of material, hurled outward into space at speeds that can reach over 1 million miles an hour. These eruptions are common enough that solar physicists track a strong one aimed directly at Earth can disrupt satellites, threaten astronauts, and occasionally knock out power grids on the ground. But a coronal mass ejection doesn't just affect the inner solar system. It keeps traveling, plowing outward through interplanetary space, pushing against everything in its path, all the way out past Jupiter, past Saturn, past Neptune, and eventually all the way out to the very edge of the sun's influence itself. That edge is called the Heliopause, the boundary where the constant outward pressure of the solar wind, the sun's own particle exhaust, finally loses its fight against the pressure of the interstellar medium pressing in from the other side. On August 25th, 2012, Voyager 1, launched all the way back in 1977, crossed that boundary and became the first human-made object in history to leave the sun's bubble entirely and enter true interstellar space, the region between stars, a place no probe, no instrument, no human-built device had ever occupied before. And that's exactly where things got strange. Because when a coronal mass ejection's shockwave, traveling far behind the initial eruption but carrying enough force to keep pushing outward for months, finally reaches that same region of interstellar space where Voyager 1 now sits, it slams into the thin, cold plasma drifting between the stars, and it does something nobody fully expected before Voyager 1 was there to measure it directly. It makes that plasma ring. In October and November of 2012, and then again in April and May of 2013, Voyager 1's plasma wave instrument, a piece of hardware built using 1970s technology, originally designed to study the plasma environment around Jupiter and Saturn, picked up exactly this kind of event, a sudden burst of oscillation in the electrons surrounding the spacecraft, triggered by a shock wave that had left the sun more than a year earlier and finally caught up with Voyager 1 out in the true dark of interstellar space. Don Gurnett, the physicist at the University of Iowa who served as principal investigator on that instrument for decades, described what the team was seeing in strikingly direct terms. Most people, he said, would have assumed the interstellar medium was smooth and quiet. Instead, these shockwaves turned out to be far more common than anyone expected, exciting the ionized gas out there into a resonance nobody had directly measured before. Ed Stone, the mission's longtime project scientist at Caltech, put it even more plainly. The shockwave, he explained, was causing the interstellar gas itself to sing or vibrate like a bell. That word wasn't just a poetic flourish for a press release. When NASA and JPL took the raw data from that plasma wave instrument and converted its frequencies into a range humans could actually hear, the result was an eerie, warbling, genuinely otherworldly whistle, rising and falling in pitch as the density of the surrounding plasma shifted in real time. NASA released those actual audio clips publicly, letting anyone listen to what the edge of interstellar space sounds like, when it's excited by a shock wave that started as a violent eruption on the surface of our own star. That's the literal, documented version of "a star screamed and Voyager heard it." The sun erupted. The resulting pressure wave crossed the solar system, kept going into true interstellar space, and by the time it reached Voyager 1, the plasma around the spacecraft was ringing loudly enough, in a frequency range converted for human hearing, that it genuinely sounds like something crying out in the dark. Here's why that ringing matters beyond how eerie it sounds. The pitch of that ring directly tells scientists something they'd otherwise have almost no way to measure: the density of the plasma surrounding Voyager 1 at that exact moment. Higher density plasma oscillates at a higher frequency, lower density plasma rings lower, and by carefully analyzing the pitch of each event, researchers could calculate for the first time in human history exactly how thick or thin the material between the stars actually is in that specific region, a measurement nobody had ever been able to take directly before Voyager 1 got far enough out to feel it happening in real time. And the story didn't stop with just 3 events caught in the early 2010s. In a study published in December 2020, a team led once again by Gurnett and his colleagues reported something even stranger riding along on the back of these solar shock waves: bursts of cosmic ray electrons, accelerated to nearly the speed of light, arriving at both Voyager 1 and Voyager 2 within days of each other, evidence that the shock wave from a distant solar eruption was reflecting and accelerating particles along interstellar magnetic field lines in a process that had never been directly observed happening outside our own solar system before. These energetic electrons acted almost like an advanced scout, racing ahead of the slower plasma wave signal, giving researchers an early warning that a shock wave triggered by an eruption on the sun more than a year earlier was about to sweep past. Gurnett was direct about why this mattered. The idea that shock waves accelerate particles wasn't new on its own, but detecting it happening in the interstellar medium specifically, a fundamentally different environment from the solar wind closer to home, was something genuinely new to physics. Then, in 2021, researchers led by Stella Ocker, analyzing years of accumulated Voyager 1 data, found something that didn't depend on any single dramatic eruption at all: a persistent, extremely faint, narrowband signal that had been quietly present in the spacecraft's plasma wave data continuously since 2017, humming along steadily in the background between the occasional louder, shockwave-triggered events. Unlike the dramatic bursts tied to specific solar eruptions, this quieter signal never really stopped. Ocker described the challenge of studying interstellar density up until that point in blunt terms. The loud, shockwave-driven whistles only showed up roughly once a year, which meant the map of interstellar plasma density scientists had built from them was, in her words, kind of sparse. The newly identified persistent hum changed that, giving researchers something closer to a continuous, occasional snapshots triggered only when the sun happened to throw a strong enough tantrum to send a shockwave that far. Comparing that persistent signal to the sudden dramatic bursts is genuinely useful for understanding what Voyager 1 has actually been doing out there for over a decade. Think of the loud, shockwave-triggered events as something closer to distant, occasional thunder, a sudden dramatic reaction each time a violent eruption on the sun finally sends its pressure wave far enough to disturb the plasma around the spacecraft. The persistent hum, by contrast, is closer to a constant, quiet rainfall, always there in the background, letting scientists track the slow, ongoing texture of interstellar space, even when the sun isn't actively throwing anything dramatic in Voyager's direction. Together, the two signals gave researchers something no model built entirely from Earth had ever been able to produce: a genuinely continuous picture of what the space between stars is actually doing, moment to moment, gathered by an instrument sitting directly inside it. There's a reason this entire phenomenon has become more relevant again recently, rather than fading into old news. The sun runs on an 11-year cycle of activity, swinging between quieter stretches and much more turbulent ones, and the most recent solar maximum, the peak of that cycle, arrived right around 2024 and 2025, bringing with it a sharp increase in exactly the kind of violent coronal mass ejections that eventually produce these shockwaves. Researchers studying Voyager's ongoing data have noted that eruptions of this kind should become noticeably more frequent as that peak activity plays out, meaning more of these shockwaves are currently working their way outward through the solar system right now, on a journey that takes well over a year to cross the enormous distance separating the sun from where Voyager 1 currently sits. Some of what left the sun during that recent peak in solar activity almost certainly hasn't finished its journey yet, meaning Voyager's plasma wave instrument may still have more of these ringing events left to catch in the months and years directly ahead, assuming the spacecraft itself keeps functioning long enough to hear them arrive. That's not a guarantee anymore. Voyager 1 runs on a set of radioisotope thermoelectric generators that convert the heat of slowly decaying plutonium into electricity, and that decay never pauses, never waits for a good moment, steadily draining a fixed, irreplaceable power budget that has been shrinking every single year since 1977. Engineers have already been forced to permanently switch off several of the spacecraft's original scientific instruments simply because there wasn't enough power left to keep everything running at once. Brutal, one-way decisions made years in advance, since there's no way to ever turn an instrument back on once the choice is made to shut it down for good. In 2025, engineers did manage a genuine win against that decline, successfully reactivating one of Voyager 1's backup thrusters after more than 2 decades of complete inactivity, buying the mission a bit more stability in how it keeps its antenna pointed back toward Earth. But that kind of success only delays the inevitable. Sometime in the early 2030s, by most current estimates, the power will finally drop below whatever minimum threshold is needed to keep any instrument running at all, including the plasma wave receiver that's been listening for these solar screams since before most of the scientists currently studying its data were even born. There's also a genuinely open, still unresolved piece of this story that researchers have been candid about not having fully nailed down. The recent, more detailed look at Voyager 1's data has revealed that the boundary it crossed back in 2012 isn't the simple static wall early models assumed. Observations gathered since then show ripples and perturbations in the actual shape of the heliopause itself, subtle evidence that the boundary flexes, pulses, and shifts over time rather than sitting fixed in one place, and that the region just outside it carries a stronger, hotter, more energetic charge than anyone predicted before Voyager 1 actually got there to measure it directly. Scientists studying this data have openly acknowledged there are still basic questions they can't yet answer with confidence, whether this energetic boundary looks the same in every direction, since Voyager 1 and Voyager 2 crossed it at different points and their measurements don't perfectly agree, and whether what the spacecraft is detecting today will still look the same years from now, or whether the whole structure is genuinely as variable over time as the recent data suggests. None of this means anyone on Earth is in any danger from a coronal mass ejection screaming its way across interstellar space. The distances involved are so vast that a shockwave leaving the Sun and finally reaching Voyager 1 takes well over a year just to cross that stretch of interplanetary and interstellar space, and whatever effect it has out there stays out there, over 15 billion miles from home with zero physical consequence for anything happening back on Earth. What makes this genuinely remarkable instead is the simple, almost improbable fact that humanity has a working instrument sitting directly inside the environment where this is happening, close enough, and sensitive Sun's own violence finally arrives and sets the space between the stars ringing. It's worth understanding exactly how a stream of raw electromagnetic data becomes something you can actually put in headphones and listen to, because the process itself is a genuinely clever piece of scientific translation, not some artistic liberty layered on top of real science. Voyager 1's plasma wave instrument doesn't record sound in any conventional sense. There's no air in interstellar space for sound waves to travel through the way they do on Earth. What it actually measures is the oscillation of electrons in the surrounding plasma, vibrating back and forth at specific frequencies, determined by how densely packed those particles happen to be. Those oscillation frequencies fall within a range that, purely by coincidence, sits close enough to the range of frequencies human ears can perceive that scientists can take the raw electric field measurements, shift them slightly, and play them back as an actual audio waveform. The eerie, rising and falling whistle you hear in NASA's released clips isn't a sound effect added afterward for dramatic effect. It's the literal, direct translation of how fast those electrons were vibrating at each moment, played back at a pitch a person can actually perceive. That distinction matters because it's exactly whistle scientifically, not just describe it poetically. A higher pitched whistle means the electrons were oscillating faster, which corresponds directly to a denser plasma environment surrounding the spacecraft at that specific moment. A lower, more drawn-out tone means a thinner, more sparse plasma. By tracking how that pitch rises and falls across the several days or weeks each event lasts, researchers can build an actual quantitative map of how interstellar plasma density changes in the specific region Voyager 1 happens to be passing through, all from what sounds, to an untrained ear, like nothing more than a strange, ghostly moan drifting up and down in tone. It's also worth putting this particular kind of space sound into context alongside other, more widely recognized examples, because Voyager's interstellar whistle isn't the only time raw spacecraft data has been converted into something audible, though it remains one of the most physically direct. Recordings of Saturn's radio emissions, captured decades earlier by the Voyager spacecraft during their flybys of the ringed planet, and later studied further by the Cassini mission, produced their own eerie, crackling tones when translated activity tied to Saturn's own powerful magnetic field and auroras. Jupiter's magnetosphere has produced similarly strange, chirping recordings when its radio emissions get converted the same way. What sets the interstellar recordings apart from all of those is where they were captured. Every other example comes from an instrument still, safely inside the boundaries of our own solar system, listening to a planet's own magnetic environment from relatively close range. Voyager 1's interstellar whistle was recorded from a region no other instrument has ever occupied. sound, in the loosest possible sense of the word, captured from literally outside the only home our civilization has ever known. That distinction is also exactly why NASA and JPL have leaned into language like singing and treated these recordings as something worth actively sharing with the public rather than filing them away as a routine technical footnote buried in a research paper. A spacecraft, launched in 1977, designed using slide rules and technology that predates the modern personal computer entirely, ended up giving humanity its first direct audible connection to a part of the universe that had, up until that exact moment, only ever existed as a theoretical concept in physics textbooks and computer models. Nobody on the original Voyager engineering team, focused on getting usable photographs of Jupiter and Saturn before the mission's expected end in the early 1980s, was thinking about capturing the sound of the space between stars. That outcome only became possible because the spacecraft simply refused to stop working long after everyone involved expected it to. That refusal to quit is really the through line connecting every part of this story back to where it started. Voyager 1 was never built or funded with the expectation that it would still be operational, let alone scientifically groundbreaking, 5 decades after launch. Its mission planners in the 1970s were focused entirely on a 4 to 5 year flyby tour of the outer planets. A well-defined finite goal with a clear beginning and a clear expected end. Every single discovery that's come after that original plan concluded the Heliopause. Crossing in 2012, the shockwave-triggered plasma singing captured that same year and the year after, the cosmic ray electron bursts identified in 2020, the persistent background hum found running continuously since 2017, and the ongoing evidence of a turbulent, rippling boundary still being pieced together today has been, in the truest sense, bonus material. None of it was guaranteed. All of it depended entirely on a roughly 50-year-old machine continuing to draw enough power and stay coherent enough to keep listening long after anyone reasonably expected it to still be capable of hearing anything at all. And there's a genuinely sobering piece of arithmetic sitting quietly underneath all of this that's easy to miss while focusing on the eerie sound itself. Every one of these plasma-singing events that Voyager 1 has ever caught began with an eruption on the sun that happened well over a year before the spacecraft actually detected anything. That means the recordings NASA has released, the ones that sound like something crying out in real time, are actually old news by the time anyone on Earth ever hears them, echoes of a solar tantrum that had already finished happening long before the resulting shockwave finished crossing the unimaginable distance separating the sun from true interstellar space. Every future recording will carry that same built-in delay, a signal from the past arriving in what feels, to us, like the present. Whatever additional eruptions the recent solar maximum has already sent outward are still out there right now, somewhere in transit, still years away from finally reaching whatever's left of Voyager 1's ability to hear them arrive. Gurnett, who spent decades of his career on this exact instrument before he passed away, in 2022, spent much of that time arguing that the interstellar medium deserved to be studied as an active, dynamic environment rather than a settled backdrop, and Voyager's plasma-singing data became some of the clearest proof he ever got that he was right. So here's the real shock. Once you strip away the fake urgency and let the actual story sink in, the sun really did scream in the most literal physical sense that phrase can carry. A violent eruption on its own surface, throwing plasma outward with enough force to travel for more than a year across a distance so large, it makes the entire inner solar system look small by comparison. And Voyager 1, a machine built using technology from before the personal computer existed, running today on a fraction of the power it takes to light a small appliance, genuinely did hear it, converting a raw electromagnetic signature into an actual, audible, eerie, ringing tone that NASA recorded and released for anyone curious enough to listen. It's not a metaphor stretched for a headline. It's a 50-year-old spacecraft, sitting alone in the space between the stars, still picking up the aftershocks of its own home star's temper, more than 15 fact, and still, for now, finding a way to tell us about it.